All right. Good morning, everyone. I had another note. Where did it go? Nope, that was it. Never mind. Okay. But I got to do this. Today's the 7th. All right. So at this point, testing the test 2 has closed. So if for some reason you didn't take that test, you have missed your opportunity. Those of you who did take it, for the most part, did excellent. I saw A's, B's, and C's, so I'm not going to be dissatisfied with those results. For the most part, those of you who are really doing all of the homework, or at least almost every problem, you tend to be getting the A's and B's. And then, the opposite statement would be on the C's, but it's not 100% consistent. I'm not going to say that across everyone. And it's a small class size, but anyways, you're doing good, all things considered. So keep up that pace. Keep doing your best. Sorry, I was about to cough, so it's stopping me. Keep putting the effort in your 9 hours a week in addition to class time. Previous due dates, it's just 4.1 due on the 9th. We said that we covered 4.2 last time, but I wasn't going to give you official homework on it. I'm not going to give you official test problems on it because those problems can be a little more complicated, and really the complications are just the time-consuming element to it. Because if you want to have the widths of those rectangles be small enough to get you an accurate answer, you're doing a ton of arithmetic. And the thing about 4.2 is it's an amazing section, it's an amazing technique, but you want computers to be doing the processing for you with a problem like that to get accurate answers with your delta x's or widths, as you will. It'd be like a 0.01 or a 0.001 to then be adding hundreds and thousands of little rectangles to get a super accurate answer. But we did at least see that, hey, we were in the ballpark of an area with those estimates. I mean, it was, the 1 or 2 examples we did were off by like 10 or 15. That's not great, but it was in the ballpark at least. Okay, so the last thing I want to mention before starting out with 4.3 today is that my cough is coming back. Thursday the 16th, this really shouldn't affect you. Our class is going to be pre-recorded, and I'm probably going to do that on Wednesday the 15th. I have a family event that I really need to attend on Thursday, so I can't teach on Thursday. But with this format, knowing that ahead of time and not just being sick and missing an opportunity, I can go ahead and on Wednesday record the lecture that I would have been giving on Thursday. I can upload it to YouTube, and then boom, everything is normal, except if you wanted to ask a question live during the lecture, that's the only opportunity that it's missed. So you shoot me an email, and then I'll answer you as soon as possible. So this means that if you want to watch Thursday's lecture early to go ahead and get it done, you can just check, probably Wednesday, no later than 5 p.m. I should have that up, I would say. I got to do this for both my classes. So, it might be 1 p.m., it might be 3 p.m., it might be 5 p.m., but you will see it at some point on Wednesday. So if you want to watch this class at a normal time, then on Thursday the 16th at 11 a.m., you just go to Canvas, open the YouTube link, and watch it for 2 hours. If you want to get it done early or watch it a little later, you have that opportunity as well, but remember, you are supposed to watch these. So again, this really shouldn't affect you at all. The only small effect is you can't ask a question while I'm teaching, but you can still shoot me an email, and I would be happy to answer that. And then if it's an email that I need to then say, oh, I have a tiny correction or something like that, I can then just distribute that email to everyone. So if there's no questions on that issue, we will get into 4.3. Bad habit. Areas and definite integrals. Let me go ahead and give myself lots and lots and lots of space so I don't end up with that formatting issue later that you've seen me have dozens of times, maybe not dozens of times, but several times. So as a reminder, indefinite integral is for a given function f of x is capital F of x equals the integral symbol, then the original function, and then you throw that dx in. So again, the integral symbol and the dx go in every single one of these types of problems. And we said that we don't have to give you an original function. We could give you a derivative, and then you just say the little f is the integral of the f prime dx. Or for a given function f prime of x, then it would be a little f of x is equal to integration symbol, and then the f prime of x dx. And we saw in the last section that this integration formula is very, very, very related to the area under a curve. The indefinite integration was related to the area under a curve. But we didn't exactly, I don't want to say this, we didn't give out every single layer of detail to it. We just did kind of this observation where, okay, we went from 0 to 5 on something, or 0 to 4 on something, whatever it might have been. And we saw that if you plugged in the largest value into the integrated function, that we got what happened to be the area under the curve when we did the rectangle and the triangle. But that was because we started at 0. We don't have to start at 0. We can start at 1 or 2 or 9 or 15 or -3. So we have to generalize a little bit more. We can't just say to plug in the largest function value into the capital F or the integrated function, and that gives you the area under the curve. There's a little more subtle detail to it. So more specifically, the integrated formula, the integrated function, excuse me, gives you the area under the curve from x equals 0 to x equals, let's just say b. If you insert b into the integrated function. What I'm saying here is we got a graph. And our curve looks something like this. So this is the regular function, not the integrated function. And let's say we have just a b right here. Draw a little dotted line there, and then here's a point that was a little high. Here's the height f of b, little f of b. So the area from 0 to b is equal to capital F of b. That's not little f, that's not the same thing. This is little f of b. This height right here was the actual function value. This would be integrating the function and then plugging it in to b. Now you don't plug the b into the function and then integrate. You have to integrate the function and then plug it in. So the area under a curve is represented by plugging in Again, only if you're starting at 0. Is just plug in the right-hand x value into the integrated function. But what if you want to start it somewhere besides 0? Think about separate areas. So let's say our goal is to find the area from A to B. So same, just random function curve. This is our f of x. But now we want to go between A and B. So this would be the area between A and B on the x-axis. So check this out. Let's do 2 different integrals. Think about what capital F of A is, capital F of B is, and what simple operation could lead you from these 2 areas to 1 area. Again, we don't want to go from 0 to B. We have that picture up here. We want to go from A to B, but just plugging in B does the area from 0 to B. If you plug in A, it does this area from 0 to A. So let's dissect this. Let's show what this writing on the right side I just did. Let's show what both of those would be. So I'll do that in blue. Black for this. Black for the function part. So there's our f of x. Here's A. Here's B. And I'm going to show another one. Don't worry about if these functions don't look exactly the same. And then A seems to be about the peak. B seems to be about the valley. So on the left one, this left image, I want to show you what the area is going up to A. This area right here would be represented by f of A, because we're going from 0 to A. If I do f of B, it covers all of this area. Not just up to A, not between A and B, all the way from the y-axis up to B. So I showed you where A and B were in each of these graphs, but B was irrelevant for the first one, A was irrelevant for the second one. Now there's really not a lot to do from here, believe it or not. Think about what f of A is, which is whatever this number area would be. Think about what f of B is, which would be this area. And what simple operation could lead you from these 2 different areas? The x looks a little funny. To 1 area between them. One simple mathematical operation. What could you do with f of A and f of B? What could you do with these 2 values to get this one? Well, let's pretend that f of A, this area was 10. Let's just pretend for a hot second. So in this green, we're going to pretend. If we pretend that this area was 10, and if we pretend that this area is 40, Again, all of it, all of it, all of it. So this little area here is 10, and then this entire area all the way up to B is 40. So again, I'm talking about this whole area, that's the 40. And then this little area, ooh, that was a terrible, terrible line. And then this area is the 10. So this is where I'd love for someone in class to say, but I know it's a different situation. If this is 10 and this is 40, then if you wanted to know what this extra area here is, the area from A to B should be 30. Because this was 10, and then whatever is here is just being added to the 10 to give you a total of 40. Well, we're thinking backwards though, so instead of adding, guess what we do? We subtract it. If you took 40 and 10 and subtracted them, you'd get, guess what? 30. So this is just the difference of the two areas. Which gives us what is known as the fundamental theorem of calculus. The fundamental theorem of calculus. It's kind of interesting in math classes. You tend to get a fundamental theorem of something. When you're in pre-calculus, you get the fundamental theorem of algebra, which states that for a polynomial, you can only have as many equations as the largest degree, as many solutions to the equation as its largest degree. The fundamental theorem of algebra isn't learned until you've done like 2.5 years worth of algebra. That's kind of weird, right? If it's fundamental, why wasn't it the first thing you do? Well, the fundamental theorem of calculus, this is, I mean, week 7, right? And now we're just getting to the fundamental theorem of calculus. It's not saying it's the first thing we need to do. It's just so important that it's fundamental to an entire subject matter. So yeah, we were able to do a lot of stuff before. We were able to do derivatives, we were able to do limits, but in terms of the other side of calculus, this area side, this is the fundamental theorem of it. So the fundamental theorem of calculus says that the area under a curve between two x values, a and b, is the following. And there's two different ways to write this. You have your integration symbol, but now you put numbers or letters for now on the bottom and top of it. So these a and b are generally numbers going between, say, 1 and 10, or 2 and 5, or 0 and something, or -6 and +6. And then you have your little f dx. So when we write our integration with numbers below and above it, like this, that says we're actually finding an area under a curve. Without these numbers, we're not necessarily finding the area under a curve. We're just integrating for other reasons. When you do it, this is equal to the integration at the right value, which would be the area up to that value, starting at 0, but then you subtract the area up to the first value. See, that's what we do. This right here, if this is 40, this area has to be 10, this area has to be 30 to make the whole thing 40. So if you have the whole thing as 40 and you know the first thing is 10, you subtract it off to get the 30, the area that you actually want. So this is known as the definite integral. Indefinite means you're not finding an area. Definite means you are. And a lot of applications, we're usually doing the definite integral. So this is one way that things are written, but sometimes people want to have some extra notation in the middle. Oops, wrong color. So in case you ever see this, and you will with me, the capital F with a vertical line behind it and then A and B. This means the same thing as exactly what you see on the right-hand side. F of B minus F of A. All capital Fs, all integrated formulas. So you can say that the integral from A to B of a little f is equal to big F evaluated between A and B. When I said there were two versions of this formula, that's the two versions. Because this thing right here is the same as the subtraction. So this vertical line and then the A and the B, that's just signifying to plug in the upper and lower limits. That's what those are known as, the upper and lower limits or upper and lower bounds. So finding an area under a curve is not really any more complicated. You still have to do an integration. It just means you're going to be plugging in two values into it and subtracting what you get. So again, integrate, then plug in. Integrate and then plug in the upper and lower limits. Some people will say left and right hand limits. That works too. All right, so let's try this out. Yeah, I can fit an example here. On the area under the given curve as a function. For A, we've got the integral from 0 to 3 of x squared dx. I said I'd do an x squared first. I think I was going from 0 to 5 in the last class's lecture, but that's okay. When we were doing the approximation, that is. And in fact, I can do this from 0 to 5 really quickly after the fact. So this is the original function. This is the lowercase f, the x squared. To find the area under the curve, you have to integrate this. So the 0 and the 3 don't come into play yet. We're going to go ahead and integrate the x squared. So we're going to apply our power rule. We add 1 to the exponent, and then we divide by the same value. So x cubed over 3. Adding 1 to 2 is 3, divide by the same value. Now, I'm going to do this one and only one time. When you integrate, you usually have this plus c, right? So I'm going to put it here for now, but you're going to notice something cool at the end. So we're evaluating this between 0 and 3. This is the way I like to do things. Just make my c a little nicer. There we go. So x cubed over 3 plus c, and we're evaluating between 0 and 3. So that was this extra little notation I mentioned here. I was also supposed to do this in red, but oh well, no big deal. Okay, so plug in the upper limit first, then do a subtraction and plug in the lower limit. This is the function. This is all we can do. We can't even clean this up. So we're going to plug in the 3. So equals 3 cubed over 3. So this is what became the 3. The other 3's are just coincidentally there. Plus the c. Then we go minus. So this was the f of 3. This right here would be capital F of 3 in theory. Now we got to do the lower limit. So we do f of 0. We're just plugging 0 into this thing. So 0 cubed over 3 plus c. And this is where I would leave this in class and say, does anyone think anything's wrong here? And then hopefully someone says yes. So this right here was the capital F of 3. This right here is the capital F of 0. And we're supposed to be subtracting those things. It's supposed to be this thing minus that thing. But there's extra terms. That's not being subtracted appropriately unless we wrap it in parentheses. This happens 99% of the time, that you need a parentheses around the second one. So let's see what we get. 3 cubed is 27, so that's 27 over 3. I'll show the extra work. Plus c. Distribute the minus. 0 cubed is 0, so 0 cubed over 3 is 0. I'll write that for now. And then minus c. Well, 0 divided by 3 is 0. That's gone away. 27 divided by 3 is 9. And c minus 0, c cancel. That c and this c cancel. So the answer is 9. The area under the curve from 0 to 3 is 9. Please note, the c's always, 100% of the time, cancel. If you're going to do your integration with the c there, when you actually plug in your upper and lower limits, that c will be positive for the first one, negative for the second one. They will always cancel, which gives us the very super important memo: never use c when doing definite integrals, as it is pointless and always cancels. You don't have to do it. And I alluded to this fact last time. I was like, you know, we see that area there, but there was still a c. What's up with the c? This is what really happens with the c. So those capital F's, when you evaluate them, like so, they cancel each other out. So again, the c is only necessary for indefinite integrals. So you have to be careful as a calculus student. If I give you a problem that's indefinite, you better have a c. If I give you one that's definite, you can skip it if you like. You can just always put them in there, but then you're going to always see this tedious cancellation. I suggest that you practice this dozens and dozens and dozens of times to get used to when you need a c and when you don't. All right, so before we get to B, let's just do an alternative version of A. Let's go the integral from 0 to 5 of x squared dx, because that's the one I believe that we related to back in 4.1, or 4.2, excuse me. Let me see. I just want to confirm that. X squared, yep, from 0 to 5. So we did an approximation and we found one of the approximations to be 30 when we did an under approach. Then we did an over approach and we found the approximation to be 55. And I even gave you what it really is as a spoiler. But now let's see what it really is. So a left-hand rectangle approach said the area was about 30 with a width of 1. So, I mean, that's okay, but it's really not that accurate. Using a right-hand approach with a width of 1, the area was about 55. And again, if you want more accurate areas, make these widths 0.1 or 0.01 or 0.001, whatever you want to do that's smaller. The smaller they are, the more rectangles you have, the more accurate of an area you get. But we're not doing any of that jazz. We're doing the exact fundamental theorem of calculus. So, well, we already know the integral is x cubed over 3. We now know we really don't need the plus c, so I'm not going to write it anymore, ever again, when I'm doing definite integrals. And we're just going between 0 and 5. So we plug 5 in the first time. That's 5 cubed over 3. So that's the f of b, if you will, capital F of b, minus, now plug in the 0. That's 0 cubed over 3. 5 cubed is 125 over 3 minus, well, that's 0. So 125 over 3 is the exact area, which if you convert that to a mixed number, that's what, 41 2/3. So that is the exact area under the curve from 0 to 5. It's about 42. The approximations we had, the under was 30, excuse me. So when we did the left-hand one, we had a 30 as in our approximation. When we did the right-hand one, we got 55 as our approximation. What's cool is, and this isn't always super accurate, this, depending on the polynomial, this doesn't have to be super close, but if you average 30 and 55, I said this is kind of a classic way of getting a better approach. If I then divide that by 2, we get 42.5, which the real area was 41 2/3. This is only off by 1 now. So by averaging the lower version and the higher version, we actually get a much more accurate one. Now again, this doesn't have to be it doesn't have to be significantly accurate. It could still be a ways off, but it is usually the best of the three. Usually, it depends on the polynomial. If you've got some super crazy, wacky polynomial that's all over the place, it wouldn't bend back. That was an error. But if it's all over the place, it doesn't have to be great. But again, for us, we're not a true calculus class. We're not doing numerical methods. So don't worry about that idea. But it is still cool to see, and I think you can appreciate that. Okay. So again, this is our primary focus in here. Doing integration formulas like power rules, logarithm rules, exponential rules, and then some fancier techniques we'll have in coming sections. So getting a function and then just jamming 2 numbers into the function to get the answer. That's it. It's just arithmetic from here. Now, you're going to have fraction arithmetic to handle. Remember, you're supposed to be able to do this stuff without calculators. So make sure you know how to add and subtract your fractions. That is going to be a very common issue. All right, B. Let's go with the area under the curve from 0 to 5 of x dx. I'm curious, how far did I go on the last one? Oh, my calculator symbol looks different. This laptop must have updated. That's funny. Either that or I'm crazy and misremembering, but I'm pretty sure that looks different. And I know this computer reset and installed Microsoft Edge or whatever they're calling the abyss that was Internet Explorer now. So I'm just curious how far we went on this one. Here was our line. We went to 4. We're just going to go to 5 this time. And we knew this one was exact. We found that and we showed that it was exact. So hopefully you have enough faith at this point to trust me. So now we're going to do the area from 0 to 5 under the curve of x. Now I'm starting these at 0. You don't have to. This formula allows us to start at any value and end at any value. I'll start doing different values next. Don't worry. So we go ahead and integrate. We take this x, which is really x to the first. That's not a prime. That's an exponent of 1. So we're going to add 1 to that and get 2, and then divide by the same value. This would be x squared over 2. That is the antiderivative of x. Now, we don't put the dx anymore, and because of the limits, we know we're finding an area. There's no c. We just go, hey, we're evaluating this from 0 to 5. That tells us the window of the area we're finding. So we plug in the 5. That would be 5 squared over 2 minus, plug in the 0. 0 squared over 2. And these don't have multiple terms, which is why I didn't need a parentheses around this. It's not wrong to do that, but you don't need it. 0 squared is 0. 5 squared is 25. So that's 25 halves minus 0, which is just 25 halves. Or as a mixed number if you prefer, 12 and 1/2, or as a decimal, 12.5. Unless my math lab is specific, it should accept all 3 formats. If you ever give an answer on a test that is correct, but just in a format they didn't want, you can let me know, and I'll give you full credit. I do not care 1 iota if your answer is a mixed number or a improper fraction or a decimal. If it's right, it's right. If this was a pre-algebra class and the whole point is to understand the differences of those 3 versions, that's another story. But we're clearly not in pre-algebra. All right. So B in particular, this is one you could actually check geometrically. You could find the area, excuse me, under this curve using geometry. And I'm not going to show that work. I will point out what it looks exactly like, though. It looks exactly like this, except you go to 5. So you'd end up, here's your graph of x, you go right one, up one. If you don't know how to graph x, that terrifies me. So there's the line of y equals x, but you're just going up to a height of 5 instead of 4. So you have a width of 5 and a height of 5. 5 times 5 is 25, but you half that and you get 25 over 2. That's the area of a triangle, 1/2 base times height. So 1/2 times 5 times 5. So I said it, but I didn't show it. All right, let's get a little different. Let's go from 3 to 8, and let's have our function be 7. So our function is constant. We still have to have the dx at the end. Hold on, I got a cough. So this right here is a constant function. This is more similar, just going back to previous problems, to this one. Sorry about that. But this was the function with a height of 15, and we even had this be a real life kind of example. So this function had a height of 15, and it ended up drawing a rectangle. We could do that geometrically. We're skipping all that though. We're doing the calculus. So this is a horizontal line with a height of 7. I'm not giving you a reason why it's 7, it's just 7. And we want the area under the curve from 3 to 8. So we just integrate. We integrate the 7. The integral of a constant is the constant times x, because the derivative of 7x is 7. So this was one of the 4 or 5 formulas we gave you back in 4.1. We had the power rule, we had the constant rule, which is actually an exception of the power rule. I technically don't even have to give you this. I could just give you the power rule. We had the natural log rule and the natural exponential rule. And then an alternate version of the natural exponential is an alternate version of the exponential rule as well, where there was a coefficient in the top. So that's why I said arguably 5 formulas. Now we would normally do a plus c here if this was indefinite, but it's not. So we don't, because it would just go away. We're evaluating this between 3 and 8. So we just take the x's and make them 8 and 3 with a subtraction between them. So 7 times 8 minus 7 times 3. This is the upper limit minus this is the lower limit. 7 times 8 is 56. 7 times 3 is 21. And 56 minus 21 would be 35. If you don't trust that, here is the horizontal line with a height of 7 that represents 7 as a graph. Here's 3 on the x-axis. Here's 8 on the x-axis. This is the area we were finding, which is a rectangle. So it should be the vertical length, which we start at 0 and go to 7, times the horizontal length, we start at 3 and go to 8, which is 5. And guess what? 5 times 7 is 35. Again, these super ridiculously simple examples like 7 and x for b and c, you can use geometry to get the areas of them. Because this ends up forming a rectangle. This ends up forming a triangle for b. This ends up forming a rectangle for c. But for problems like a, x squared, when you drew that picture down here, when you draw polynomials that bend, there's no formula that gives us the area of this bendy part to these straight parts, which is why calculus is needed, especially as the functions get more and more complicated. All right, so let's keep going. D. The integral between -4 and +5 for the function x cubed. And the dx is just part of the integration symbols. So x cubed, we can power rule this. Add 1 to the exponent, divide by the same number. That gives us x to the 4th over 4. There's no coefficient of drag. There's no pluses or minuses. That's it. Do we need a plus c? No, we don't need a plus c because we're evaluating this between a left and a right endpoint. So we can't ignore it. You can still put the c in there as long as you don't only put it once when you get to the evaluations. It should be there for both of them so they cancel. So plug in the 5. You get 5 raised to the 4th power over 4. And that's it for plugging in the 5. Now plug in the negative 4. Now be careful, we're plugging in a negative. You probably need a parentheses around your x because of that. Without that parentheses, this will be wrong, 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 wrong. You might think the negatives, this negative cancel. They don't. Because that negative is raised to an even exponent, which means it's going to become positive. But you still have the subtraction out front. 5 to the 4th, it goes 5, 25, 125, 625. Those are our multiples, sorry, our exponentials of 5. Again, 5 times 5 is 25, 25 times 5 is 125, 125 times 5 is 625. Then over 4. Minus, so this minus here is this minus here. Now negative 4, a negative raised to an even is going to be a positive. There's not going to be a negative inside of the fraction. We go 4. 4 times 4 is 16. 16 times 4. Sorry, I got thrown off. I was looking at something else. 16 times 4 is 64. 64 times 4 is 256. So that's a positive 256 over the original 4 in the denominator. Now you might say, oh, 4 goes into 256 perfectly, so let's reduce that. And that's a terrible idea, because if you make this a whole number, guess what? 625 divided by 4 does not reduce as a fraction. So then you're going to have a fraction minus a whole number, and you're going to have to get an LCD, and you've just gone in a full circle. So don't reduce. If all of the fractions can't reduce to a whole number, don't reduce any of them until the very, very, very end. So pause on reducing this for now. Wait until you just have one fraction, because that will avoid you having to get an extra LCD. So if you do this subtraction, 625 minus 256, that's going to be a 9 at the end. 11 minus 5 is 6, and then 5 minus 2 is 3, so 369 over the 4. This does not reduce, so that's our answer. If you want that as a decimal or a mixed number, let's see, 4 and a 3, 6, that's going to be 90, another 2 from the 9, 92 and a quarter or 92.25. Or 92 and 1/4. I'm not going to write all three. Now, if that's a fraction that's like at thirds, you don't want to write that as a decimal, because most people won't write the bar and then it's wrong. And some mathematical programs don't allow you to put a bar up there. I know my math lab at one point didn't used to, but I think now it does. So again, just something you have to be very, very careful with are your fractions. And you end up seeing a lot of fractions with this stuff. Now, how do I want to do this? Yeah, let's do it here. So I'm going to draw the graph of x cubed and represent the area from -4 to 5. Then I'm going to do 2 more examples. And I want to see if maybe first you can guess the answer off the bat. And second of all, if you can't do that, can you at least reason it out geometrically that it makes sense? So let's make this picture. And I will need, you know what? How do I want to do this? How do I want to do this? Let's put it on the next page. Save room for 2 more of these, and I'll go ahead and write what they're going to be. I'm sorry for being all over the place. I'm used to having a big old board and a TV screen and other media instead of just one thing. So this is more compressed. E will be the integral of x cubed from 0 to 5. And then F is going to be the integral from -5 to +5 of x cubed dx. All right, so before I do E and F, let's go ahead and go lower and paint the picture for D. So we were going the graph of x cubed from -4 to 5. And I can probably fit them all on this page, especially if I zoom out just a little bit. Okay. And I'll label them. It was D, E, and F. So graphs. For D, the right side of x cubed looks like this. The left side of x cubed looks like this. So this is our graph of x cubed. And we went from -4 to +5. So if this is -4 right here, +5 would have to be further away than that. So let's just say this is our +5. So the area that we just found was that. And what's unique about this problem is these areas are separated. There's a region over here, then a region over here. It's not like just one normalized looking geometric shape. This is a lot funkier than just a rectangle or a triangle, or even just the basic of the x cubed part, because I mean x squared. This looks like an x squared practically, but then this part over here is separated and it's also below the x-axis. Note that this area is below the x-axis. This means something. An area being above the x-axis and an area being below the x-axis is going to mean something, and I think we're going to be able to deduce that after we do the next two examples, do their graphs, and make some analysis. But anyways, this area from including here and here, that was supposed to be about 92 roughly. It was about 92. So same function, meaning when we integrate x cubed, we still get x to the 4th over 4. But now our left and right endpoints are different. For E, we're going between 0 and 5. Well, the 5 is the same, so that's 5 to the 4th over 4 minus. Now plugging in 0, you get 0 to the 4th over 4. 5 to the 4th is still 625. Over 4 is still there. That's a minus 0. So we get 625 divided by 4. Now 625 is bigger than 369, which means this area is bigger than the other area we just found. Specifically, 625 divided by 4 is about 156 and a quarter. So there are the areas. And then I want to draw the picture. So notice something about the numbers. When we went from -4 to 5, it was about 92. When we went from 0 to 5, when we made this a smaller region, the area was bigger. It was 156. It was almost 60 more. Excuse me, it was 64 more. Why did I write a 4 there? That's a 5. I think I was saying the over 4 at the same time. So let's see what the graph of E looks like. I mean, we basically already drew it, but we don't need the left side anymore. We're just going up to 5. So here's that same shape. Let me make it a little steeper than that, though. That was kind of crummy. Nope. Flat, 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 steep. There we go. So the area we're finding is now just this. So this area combined was about 92, but this only one of the parts of the area. So we're cutting a portion off, and yet somehow the area is now 156.25. How is that possible? This is a bigger shape, right? This is more area. This is more coloring that you would have. I'm sorry, this was more coloring than you would have to do for the second one. So why is it humanly possible or fathomable that this area has a larger number than this one, which had more segments? It has everything to do with this right here. This area was below the x-axis. So this area over here was 156 1/4, just the right side. Then this left region, whatever area that was, it actually counts as being negative. Whenever your curve goes under the x-axis any area is now going to be negative associated with that. So this left portion is a negative area, this right portion is a positive area. So again, this is a negative area, so this is like subtracting away from it. This is adding area. And you might say, well, Mr. Beckner, you can't have negative areas in geometry, and that's because this isn't geometry, this is calculus. So the x-axis counts as a divider, and when we do applications, that's where things start to tie together, that negative areas have an impact on positive areas. So let's look at F. Now with D, this side was kind of smaller, the left side was kind of smaller than the right side. Let's go ahead and paint the picture to F. Oops, wrong color. And let's see if you might be able to guess what the answer is. So we're going back to drawing both sides of this. Sorry for that little squirreliness there. And we're going from -5 to +5. So why did I write a negative there? Good Lord. Because I said negative at the same time. I'm getting much worse about writing and thinking and speaking at different speeds. So now we're finding this area. Now from 0 to 5, we already know that this little area right here, this area from 0 to 5, we know that's 156 1/4. We know that from here to here is 156 1/4 by above. Now guess what? If you go from 0 to -5, or -5 to 0, that's still the same exact shape. This height down here is the opposite of this height up here at 5. So I'm going to guess that this area right here is -156 1/4. That's my guess. Which means that the total area, these are opposites and will cancel, and thus would be 0. Because the size of this shape is exactly the same as the size of this shape. One of them counts as being a positive area, one of them counts as being a negative area, so when you add them together, they cancel each other out. This is kind of like having a loss one year and a profit the next year, where they match, so now you're just at $0. Let's see if the calculus mixed with the algebra agrees with this. So we know the integration is still x to the 4th over 4. We know that. Now we're evaluating between -5 and +5. So we go 5 to the 4th over 4 minus, little parentheses for this plug-in, -5 to the 4th over 4. 5 to the 4th is 625, so that's 625 over 4 minus -5 to the 4th is also 625. That subtraction is still in front though. Those are opposites, so they cancel. So even though, if you just thought of this in terms of geometry, this area would actually be twice of 156 1/4, which puts that at what, 312.5. But in terms of calculus, when we have positive and negative values of functions, which means when we integrate over time or over product numbers or whatever, those can still be associated with negatives in terms of an application. That's how areas can be negative. That's how areas can be 0. Yeah, in flat out geometry, there is no negative area. But in calculus, when we're dealing with applications, when we're integrating rates, you can get negatives, you can get zeros. Now you have to be careful here. Some people will always just go to the picture when they see a symmetry problem like this. Oh, from -5 to 5, it's always going to be 0. Let's do another one. Let's do the integral of x squared dx from -5 to 5. We know from 0 to 5, we already did that earlier. It was what, 125 over 3. If you draw this picture, where do I want to put it? Can I squeeze it? I'll squeeze it in over here. So if I draw this picture, x squared is all positive. X cubed, the left side goes down. X squared, the left side goes up. So here's our x squared graph. And we're going from 5 to -5. So if your teacher was a perfect artist, which that's terrible, much better. Here, I'll put the -5 here. Okay. So this is the area we're trying to find now. So you don't just say the area under the curve, because that would go infinitely into the negatives. We're going between the area under the curve and the x-axis. That acts as our other side. Do you think that the area here would be 0? Some people would say yes, because this area matches this area, so they cancel out. That's not the case. Areas are only counted negative if they're below the x-axis. This is not below the x-axis. This is not a negative area here. That's a positive area. But based on symmetry, from 0 to 5, this curve is identical. From 0 to -5, that height's identical, that curve's identical. So whatever this area is should be the same as this area. And we already know from 0 to 5, again, earlier we said it was 125 over 3. So this area, just the right side, was the 125 over 3. This is literally the same shape, just mirrored. So its area should be identical, not negative, because it's above the x-axis. If it was below, it would have been negative. See, this was negative because it's below. This is positive because it's above. So this area is 125 over 3. This area is 125 over 3. They're the same, so you can just double it. So the total area should just be 2 times the 125 over 3, which is 250 over 3. Let's see if that agrees with the actual calculus. So integrating, you get x cubed over 3, and you're evaluating between -5 and +5. So that's +5 cubed over 3 minus, use a parentheses for plugging in the -5 cubed over 3. 5 cubed is 125, so that's 125 over 3. Now this minus cubed stays minus. We still have the minus for the subtraction, so it's minus -125 over 3, which is a positive. Adding the same number twice is the same as doubling it. You get the same answer. What I'm trying to show you here is that you can use the concept of symmetry from pre-calculus at times to change your integration bounds and come up with an area. So if you know you have an even symmetry function, if the left side matches the right side with the x-axis, the y-axis is a mirror. So going from -5 to 5, you can just say, all right, well, I already know how to do from 0 to 5. Let me just double that answer, since the left area is matching the right area. Or if you're dealing with something that's cubic, which would be an odd function where the left side is the opposite of the right side in terms of height, then you could find, as long as they're symmetric, you can just say they're going to cancel each other out. But if they're not symmetric, if they're going from -4 to 5, just because you have a symmetric type of function doesn't mean you get some type of symmetric-based answer. It's only when these are opposites of each other, like in example F, when it can zero out, or in example G, where it can double out. So these are very small cases that you can use when they happen, but how often does it happen? I don't know, 5% of the time, 2% of the time, 10% of the time, a small portion of the time. But if you get one of those situations and you recognize it, why not use it if it's convenient to you? Why would I want to use the idea of doubling the area instead of this? Well, maybe I'm a student who messes up plugging in negatives all the time, or fixing a double negative situation. That could be a mistake that you make by doing it directly, versus if you use some geometric reasoning and symmetry, maybe you can avoid those simple mistakes. But again, can't always do it. 0 to 5, you can't do that because it doesn't have two sides. -4 to 5, there's two sides, but they're not symmetric. 3 to 8, there's no symmetry there. So you do have to be careful when you're going to be using it. All right, let's step it up a little. Example 2, wrong color. And we are going to do the same thing. Find the area under a curve. Given function and bounds. A, we're going to do the integral from 1 to 5 of the function dx over x. So this you might think is the power rule. You might say bring the x to the top, and then you got an x to the -1. Add 1 to the exponent and divide by the same. But -1 plus 1 is 0, and that's that one and only one case we said the power rule fails on. You can't use the power rule here. You have to go back to the natural log exponential rule. It's frozen on me. There we go. Da, 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 da. This thing is being really bad right now. There we go, finally. Probably because I've tried to open too many files. It's probably going to crash on me, if I had to guess, in the next 30 minutes, but that's okay. So we said when you have to integrate 1 over x dx, you get the natural log of the absolute value of x. And that was because the derivative of the natural log is 1 over x. But we said we had to remember this absolute value. This is something a ton of calculus students forget. If I don't tell you x is positive, you need this absolute value. If I do, then you don't write it. Now, I wrote it this way, integral of 1 over x dx, but you'll notice on this example we have here, it says the integral of dx over x. It's the same thing. If you need to rearrange this, you can. Some students do, some students do not, but these are the same thing. So the integral of 1 over x is the natural log of the absolute value of x. But we're not doing a plus c, we've got evaluations, so we draw that extra line. L, absolute value, line for evaluations, that's a lot of bars, isn't it? Make sure you understand which is which. So natural log of absolute value of x evaluated between 1 and 5. Now, here's what's cool. I don't really need the absolute value for this example because 1 and 5 are positive. So I could drop it because the answer will be analytic either way. But it's just a good habit to have. So this will be the natural log of the absolute value of 5 minus, that's the upper limit, minus the lower limit, the natural log of the absolute value of 1. The natural log of 5, I have no idea what it is. You should have no idea what it is. I have a ballpark of what it is. It's between, this number and that number. But I don't know what it is to a decimal point. Minus, but I do know what the natural log of 1 is, and you are supposed to remember what the natural log of 1 is. So this is one of the things that was in one of those introductory review chapters that you have homework and notes on that you can go back and look at any time. But the natural log of 1 is 0. As a reminder, the natural log of 1 is 0. The natural log of e is 1. You will see those over and over and over and over and over. Now, well, what happened to the absolute value of 5? Well, the absolute value of 5 is 5, so I drop the absolute value. And then the natural log of 1 is 0. We don't need to write minus 0, so we just write the natural log of 5. If you're curious as to what that number is in size, you can pull out a calculator and get an estimate. Natural log button, 5, close it. It's 1.61 or 1.6 depending on how you like to round. But that's a rounded answer. Your homeworks, your teacher generally wants exact answers. So yeah, that's about 1.6. but I don't want to see 1.6 unless it asks you to round. If it's an application, you're probably going to round it. But this was not an application, so don't you dare. B. The integral from 0 to 10 of e to the x dx. I'm also going to remind you that the natural log of 0 is undefined. You can only take the natural log of positive numbers. You can't take the natural log of a negative. You can't take the natural log of 0. Natural log is only defined for positive values, hence the absolute value needed. Because I could say to evaluate the area under the curve of 1 over x dx from any number to any number, I just can't make the upper or lower bound 0. So integrating e to the x, we go back to our formulas that you're supposed to memorize. The integral of just an e to the x is e to the x. If there was a constant coefficient up there with the x, then you'd have to divide by that as well. So we're just using the simpler one. But you can still see this one all day, every day. So the integral of e to the x is e to the x. Red. We're evaluating this from 0 to 10. So e to the 10, that's plugging in the upper limit, then minus. E to the 0, that's plugging in the lower limit. Don't you dare ever leave exponents of 1 or 0. Evaluate them. E to the 10, no idea. It's e to the 10th. Minus. Anything to the 0 power is 1. Anything to the 0 power is 1. That's the answer. That's all you can do with it. If you want an approximation, if this was an application, once again, you can pull out your calculator. E raised to the 10, close my parentheses, minus 1, and it's about 22,025 roughly. That's a big number. So the area under 1 over x from 1 to 5 was a tiny number, like 1.5 roughly, 1.6 I think, yeah, 1.6. But the area under the curve from e to the x from 0 to 10, it's twice as wide as last time roughly. But this e to the x function is so much higher than 1 over x as you move on, that that area is a much larger number. Look at the graphs of these things. Here's 1 divided by x versus e to the x. But you're supposed to remember what these look like from pre-calculus. There's 1 over x, and it's got that vertical asymptote. Here's e to the x. So if you're finding the area from 1 to 5, I mean, you're in here. You're in this tiny little region. That's not going to be a very large area. That's why it's only like 1.5. But if you're doing e to the x from 0 to 10, I mean, this thing is off the chart by the time you hit 3. Trace, 2. Wrong function. Let's hit up. There we go. 2. The height's 7.3. If I do 3, I'm already out of this window. I'm at 20. If I go to 10, the height of e to the x at 10 is 22,000 and some change. So we're way up at 22,000 by the time we get to 10, which is why this area is so massive. Because exponential curves, not curves, exponential curves grow very rapidly. 1 over x is actually a descending curve. It does not grow. It shrinks. All right. Let's do another. All of the ones we've seen so far were just single terms. Let's get into one that's got an addition or a subtraction. We need to mix this up finally. So the integral, and let's get weird with it. From e to e squared of the function x plus 1 over x dx. Now, if that was 1 over x squared, you'd bring it to the top and make it x to the negative 2. Hold on, I gotta cough again. If this was 1 over x squared, you'd bring it x to the top and make it x to the negative 2. If it was 1 over x cubed, bring it to the top, x to the negative 3. And those would be power rules. 1 over x, nope, it fails the power rule. That was the natural log rule. I'm not going to flip back to that page again. This x counts as x to the first. So when you add 1 and divide by the same exponent, that's x squared over 2. Plus, the integral of 1 over x dx is the natural log of the absolute value of x. But then we're evaluating this thing between the upper and lower limits, between e and e squared. Which is like between 2 and some change and 8 and some change, roughly. All right, let's plug in these upper and lower limits. And I forgot to switch my color. That's frustrating. When I plug in the e squared, when I plug it into this x, that's e squared squared over 2. That's plugging the e squared into here. Now let's plug it in here. So plus the natural log of the absolute value of e squared. Again, in this red ink, all I have so far is just plugging in the e squared into the previous function. Then we're going to need to subtract. So minus, and because the next part has got multiple terms, we're going to need parentheses. Now we're plugging in the e into the original integrated function. So e squared over 2. Not e squared squared anymore, so we're just plugging an e in here. And then plus the natural log of the absolute value of e. Looks like Linlell, the natural log of the absolute value of e. Extend your absolute value bars however much you have to make sure you can tell those are absolute values and not more L's or 1s. We got some simplification we can do. E squared squared, multiply the exponents. Yeah, 2 plus 2 is 4, but you're supposed to multiply them. 2 times 2 is 4. So e to the 4th. So if that had been a 2 and a 3, we'd have e to the 6th. And then over 2. Plus, well, e is a positive number. Squaring a positive number is a positive number. So I don't really need that absolute value anymore. So that's just the natural log of e squared. You might want to do this, though, so that you don't think that the 2 is squaring the natural log, that it's squaring the e instead. I can distribute the negative, so that's going to be minus e squared over 2 minus the natural log of e. Once again, e is a positive number. It's 2.71828, blah, blah, blah. So the absolute value of a positive is a positive. All right, well, there's some stuff we can do here. The e to the 4th over 2 minus the e squared over 2. You can't do anything there. You're stuck with those. That's e to the 4th over 2 minus e squared over 2. That's the first and the third terms. The natural log of e squared, this was another formula that you were supposed to have memorized back in pre-calculus. It says that if you have the natural log, and I'm just going to write this in natural logs instead of the generalized formula, the natural log of e raised to some number, some letter, let's write it as x. So the natural log of e to any exponent, this is just the exponent. That's, again, a formula that you're supposed to have memorized for pre-calculus and that is in the reminder sections from the beginning of this course. So the natural log of e squared is just 2. The idea here is the bases match. So this is like an inverse function of a function. Everything cancels except the argument being the 2. So that's a plus 2. Again, that 2 was from this because we had a natural log of an e with an exponent. So all of this jazz just cancels out, and the answer is the exponent. Minus the natural log of e, we said right here, is 1. And there is one last thing we can do. 2 minus 1 is 1. So e to the 4th over 2 minus e to the 2nd over 2 plus 1. That is the exact answer It's not a pretty answer, but exact answers don't have to be pretty. If you wanted to know approximately what it was, or if it was an application and you needed to know what exactly or what approximately it was, you just do e to the fourth, close it, divided by 2, minus e to the second, divided by 2, plus 1. And it's about 24.5. Now I'm going to show you something really cool that is not going to be that helpful to you for analytic answers most of the time, but it's a good way to check your answers if you're not sure. Go to the graph, type in your function, x plus 1 over x. Hit the graph button. So this is what it looks like. It's kind of weird. It kind of looks like an x function with a 1 over x kind of attitude with that asymptote, but instead of just flattening out this way, it then starts growing. And that's because this is basically not a composition of these two, but a transposition of these two functions. It's going to have features of both. So it's got features of a line, and it's got features of the 1 over x. All right, so check this out. Hit second, and then trace, which brings you to calculate. Some calculations for graphing. Look at what number 7 says. That's the integration symbol f of x dx. Also look at what number 6 is. So that could tell you the slope at a point. So if we do number 7, it asks you to type the lower and upper limits. So that's where we're going to type the e and the e squared. That's kind of a pain, but you still can do it. Here's my e. There's my lower limit of e. My upper limit, I got to type second e squared, close parentheses, hit enter. It actually shades it, showing you what area it's representing. And look at that decimal value, 24.604547, 24.60454. It's just got a little bit less decimal accuracy in the graph because it's got other computations it's handling. These things are ancient, so it can only do so much at once. It only wants to display so much at once. But again, in terms of actual calculus, oh yeah, okay, I typed that in and I got my answer. It was 24, blah, blah, blah. You type that in my math lab, it's wrong. You do that on a test, it's wrong. You have to have the analytics here. Remember I said for tests, you're supposed to be submitting your work to me on Canvas, which by the way, I forgot to, I made the location for it, but then I forgot to unhide it to the students basically. So that wasn't available until yesterday. So if you took the test and you haven't submitted your work, please do that today. Please go back to Canvas and you should still see the submission for test 2 spot. I have to see your work. Because for problems like this, if I give you an application and you just let your TI-83 do your work, I'm going to go back and I'm going to remove points from your test. I have that right because this is calculus. You're supposed to be showing all your work. So don't think that your TI-83 can just do everything for you. It's there to affirm your suspicions and confirm your beliefs. So when you have multiple terms, you really have to be careful when you're doing the lower limit evaluation because you've got to do the minus, you need the parentheses, and you have to distribute it. This is the #1 simple mistake that students make is they forget to distribute the negative or forget the parentheses, which ultimately makes them forget to distribute the negative. They didn't think to have it there. Let's do another one. Integration from 1 to 2 of x to the -1 minus 4x squared dx. Okay, so this x to the -1, some of you may already know this is the natural log when you integrate it. But that's not exactly how I wrote the formula out. So I know that some of you will want to rearrange this first and go integral from 1 to 2 of 1 over x and then minus the 4x squared dx. It's up to you if you need to do this rewrite or not. If you can go straight from this to a natural log when you integrate, you can skip the rewrite if you want. However, I would say it's probably a good idea to do the rewrite. That way a month later when you're looking at your notes, you don't get confused. But again, we'll be able to power rule the 4x squared. We can't power rule x to the -1 because adding 1 to -1 gives you 0. Then we divide by it and we get undefined. All right, so integral of 1 over x is the natural log of the absolute value of x. I never said anywhere that x had to be positive. Again, in your homework, they might do that. If they do, drop the absolute value. I also have a typo here. It was from 1 to 2. I wrote 1 here. That's 2. Please make sure you correct that. So the integral of the 1 over x is the natural log. Then minus, leave the 4. Integrating x squared, add 1 to its exponent and you get 3. Then divide by the same value. And now we're doing this evaluation, the upper and lower limits between 1 and 2. So now we just plug those in. So we get the natural log of the absolute value of 2 minus the 4/3 don't cancel. So 4 times 2 cubed over 3. So that was plugging in the upper limit. That was plugging in the 2. That's what we get here. I'll show the subtraction of limits in a different color. So here's the minus. So the red before and after is the upper and lower limit. Now let's plug in the 1. So the natural log of the absolute value of 1 minus 4 times 1 cubed over 3. The absolute value of 2 is 2, so we don't need the absolute value. That's just the natural log of 2. 2 cubed is 8. 8 times 4 is 32. That's minus 32 over 3. Then this is the minus sign. And can anyone point out my mistake? I did this intentionally. This is where someone would say you didn't put a parentheses around it. Remember, when you're subtracting your lower limit, you've got to make sure you put your parentheses around it. So now I'm going to distribute that negative. So minus, and then the natural log of 1, we said earlier the natural log of 1 is 0. You have to memorize that. Oops, color. But for the next term, it was originally a minus, but now there's another minus. 2 minuses cancel. So it's a plus. 1 cubed is 1. 4 times 1 is 4. So that's plus 4/3. Natural log of 2, no idea what it is. Leave it alone. Negative 32 over 3 plus 4 over 3, they have an LCD. Negative 32 plus 4 is negative 28. That's a minus 28 over 3. You don't need to write the minus 0. So that's it. You can't do anything else with that. That is the exact analytic answer. If you're curious what it is, you can put it in a calculator. I love doing this. So you get an idea what things look like. Natural log of 2, close it, minus 28 divided by 3. Negative 8.64, blah, blah, blah. So this area is negative, which means maybe there's a positive and a negative portion, but the negative area is bigger than the positive area. Or maybe just the whole area is negative. Let's see what the graph would look like. So we're doing x to the negative 1, which we said is just 1 divided by x. I could write it either way, it wouldn't matter. Then minus the 4x squared. Ooh, that looks a little weird. It kind of takes this sudden change at 0. And we're only going between 1 and 2, so let's make my window a little narrower. Let's make the x minimum negative 1, and let's make the x maximum 3. So again, because of that 1 over x, you have that asymptotic feature where it goes down to negative infinity, jumps over 0, and then goes up to positive infinity. And that's caused by the fact that we can't divide by 0. But then on the right side, it looks kind of weird. Integrating from 1 to 2, this height's not quite all the way there. Let me make my y minimum maybe negative 20. There we go. So we're just doing from 1 to 2. So we're slicing it from here to here. And it's not going to be this area down here. It's going to be this area here because we're going between the x-axis. So let's go second, calculate. Option number 7, that's our integral. Lower limit of 1, hit enter. Upper limit of 2, hit enter. It draws the shaded region that we're computing, and look at that, negative 8.640186, negative 8.640186, blah, 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 blah. So again, the answer is not negative 8.6 blah, 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 blah. It's natural log of 2 minus 28 over 3. That decimal version is not going to give you any points if it's not an application problem. And if it's a test, I'm going to go back and look for your work for all application problems of this test. Trust me, I will. And if all I see is just a decimal answer, I don't see the actual calculus, I reserve the right to take away all of your credit. I do not care that you can pull out a calculator and hit some buttons. I care that you understand all of the analytics behind it. That's what's important. All right, how much space we got? Good. E. Let's do the integral from -1 to +1. Ooh, symmetry. So maybe we could just use an argument of something. Maybe, maybe not. Let's find out. 5e to the negative x. So maybe you graph this thing and say, is there any kind of symmetry? So y equals, clear. 5e to the negative x. So 5, second e, negative symbol, x. Now let's go back to a standard zoom. And if you know anything about exponential graphs, you know they're not symmetric. It's way higher on the left, it's way low on the right because of the negative. These would be flip-flopped if it was a positive. So we cannot use any kind of symmetry argument to say, oh, I'll just do from 0 to 1 and then double it, or go from 0 to 1 and say they cancel. There's no canceling, there's no doubling. We're stuck with the calculus. And we could even go ahead and get the decimal approximation if we wanted to. We're going from -1 to 1, so we can go to the calculator part. Option 7, type -1, hit enter. Type +1, hit enter. There's the area we're going to find, and it's about 11.75. But again, I don't care about that. If it's an application, that's awesome that you have that answer, but you still have to be able to do the calculus. There's no funny rules here, really. There's no pluses or minuses, so there's no separating terms. This is just integrating e to the negative x, but the negative does throw this off. So going back to those rules, we said the integral of e to the x is just e to the x. But if there's an extra coefficient up there, you have to divide by that same coefficient. It kind of feels like the power rule in that regard, except you don't add 1 or subtract 1, you just make the exponent the bottom number. Okay. So that a is a -1 for this case. So note a equals -1 for the formula. The 5 out front, just leave it. The e to the negative x stays e to the negative x when we integrate that, but then we also have to divide by the -1. Again, because this a was a -1, the formula states that's still in the exponent, but you also divide by that value. If you don't trust this, take the derivative of what you get, and you should go back to the original 5e to the negative x. But we're evaluating this from -1 to 1. And we can clean this up. Dividing by -1 is the same as multiplying by -1. So it's -5 e to the negative x, evaluated between -1 and +1. That's -5 times e to the negative, so that's all part of the function. The -5, the e, and the negative, that's part of the function. Now I'm plugging in the upper limit, which is the +1. So I'll show the plugging in this time in blue because of the double negative situation about to happen. All right, then the minus for the subtraction of the upper limit and the lower limit. I don't need a parentheses around this because it's a monomial. All right, so now we're taking this thing right here and we're plugging a -1 in. So actually, we do need a parentheses because of the -5 up front. So -5 e. Oops, those are all supposed to be in red. -5 e to the negative, that's the function, but then we're plugging in a -1, which looks like that. Lots of double negatives. That's what I love about this problem. So what we get is, and let's go down here. The negative 5e to the negative 1, we don't really want to have answers in that format. But let's leave it for now. Let's just see what happens with the other part. So negative 5e to the negative 1. I'm not changing anything from the first part yet. These two negatives will cancel and make a plus. 5e. These two negatives will cancel and make a plus. 5e to the 1. These do not cancel and make 0. E to the negative 1 plus e to the 1 is not 0. These are very different from each other. E to the negative 1 means there's an e in the bottom. So it's negative 5 over e to the positive 1 plus 5e to the positive 1. And with exponents of positive 1, we really don't like to write them. Again, before in this format, that's not really an acceptable analytic answer because we don't like to see numbers raised to negative exponents. It's okay having a variable in there with the negative exponent. That's an okay format, but once you start plugging numbers in, you're supposed to clean them up like this. So that's something to be very, very careful of here. All right, example 3, and let's get to a word problem finally. Let's get into some of this stuff where we actually have some analysis to make. And actually before that, I want to make sure I point out something before I do the example. I'm sorry. When you're given a value as a rate, and ask for a total amount over a period of time or units of production, typically you are integrating. In other words, the total accumulation at a rate f from A to B, so f being the function, your given rate, and let me write that as f of x. I don't know why I just wrote that as f. So given so if you want to find a total accumulation at a rate of f of x from A to B, so you're given a function that's a rate, not an output. It's not telling you how many are made. It's telling you the rate of production. Then the total accumulation is equal to the integral from A to B of f of x dx. Example 3. Finding total amount tested. All right. Technician can test people for a virus at the rate of and I don't have to write this as f. I could just give you the rate. F of t equals negative 3t squared plus 18t plus 15 people per hour for a range of 0 to 6. T the number of hours after 9 a.m. How many people between 10 a.m. and 1 p.m.? So what we have here is a function that tells you how quickly these people can get some testing done. And if you've ever had a job in your life or done anything in your life, you know that you are not having the same productivity rate at 9 a.m. as at 5 p.m. if you work from 9 to 5. You're probably slowing down right before lunch. You're probably at your slowest maybe an hour after lunch, something like that. Or maybe you really get your energy back and you have peak productivity in the middle of the day. Some people have peak productivity in the beginning and just go down in productivity all day. Some people come in and are barely doing anything and just get more and more productive as the day goes on. Every person has got a different productivity rate. So this technician, his rate has been found to be negative 3t squared plus 18t plus 15. But we're saying that it's only valid from hours of 0 to 6 being the number of hours after 9 a.m. So this is only for his first 6 hours of work, or maybe this is just his full workday. Maybe he only or she only works 6 hours of the day. And that's the thing about models. We've said that very often we need to have bounds on the independent variable, because this function, if I go to say 300 hours, this function would be absolute trash in talking about productivity, because you can't have negative productivity, and plugging in 300 hours would definitely be negative in this function. So this function is only good from 0 to 6. Maybe you're curious what the function looks like. Let's graph it. So again, just curiosity for now. Negative 3x squared plus 18x. I'm not using t's in the calculator because it doesn't work that way. Plus 15. Do a standard zoom. And that's not the best picture. We don't really need to worry about negative productivity, so we don't need any negative y values. We clearly need to see some higher y values. And going from 0 to 10 is fine because we really only need to see 0 to 6. In fact, let's just go from 0 to 6. So let's maybe triple the y maximum. Let's make the y minimum 0. And let's make the x minimum 0 and the x maximum 6. Let's see how that looks. Yeah, still not high enough, so let's play with the window a little more. Maybe the y max could be 50. There we go. So this is our graph. This is our productivity rate, which is all positive. So it looks like we're doing okay at 9 a.m., but as the day goes on, 10 a.m., we're a little more productive. 11 a.m., we're a little more productive. 12 p.m., right before lunch, we're at peak productivity. And after that, we eat our lunch in this moment, and it causes us to get a little sluggish until we're finally losing energy by the rest of the day, something like that. And again, different people with different body chemistries and mental capacities have different productivity rates based on when they eat and when they sleep and when they wake and all that stuff. That's just this guy Bob right here. Now, if I pull this back, if I zoom out, you can see that eventually this curve doesn't make sense. First of all, having the curve for less than 0 doesn't make sense because we ain't going to work before 9 a.m. And if we go any later than, what's that, about 1, 2, 3, 4, 5, 6, about 6.5 hours in, all of a sudden, if I trace to 7, we're at negative productivity. So this model is no longer accurate after 6.5 hours. But again, oh, geez, that's not going to work. Let me just do this again. 0, sorry about that, 6, y min, we wanted 0, the y max I think we had at 50. Boom, there we go. So that was a rate. This does not tell us how many we've tested at a specific point, because we're testing more and more and more as the day goes on. So if in the first hour, this productivity is about 15 an hour. So we'll probably do about 15 in the first hour, maybe 16. But in the second hour, our rate's gone up, so we might be able to get 18 done the second hour. Maybe we're going to get 20 done in the third hour, maybe 30 done in the third hour. But then we're going to have maybe only 20 here, and then only 15 here, and then only 10 here. See, this is the rate we're our rate is going up and then coming down. So we're still adding people to the pile that have been tested, which is why this is a rate, not the actual number of people tested. If this was the number of people tested, that would say we've tested the most number of people right at noon, and then we've now somehow managed to test less people. So we had, let's say if this was 100 people tested, now an hour later we only have 90 people tested. That wouldn't make sense. The number of people tested has to go up. It can literally never go down. That's why this is a rate, not the actual number of people being tested. The word rate gives me a clue that we're supposed to be integrating. To find a total accumulation of something, you integrate the rate between the endpoints. So we're integrating from 10 a.m. to 1 p.m. Well, what are those t values? It's not 10 and 1 because t is the number of hours after 9 a.m. Well, 10 a.m. is 1 hour. Sorry, that should be a colon. After 9 a.m. So that makes the t1. And at 1 p.m., that's 3 more hours, so that's a t-value of 4. So we are integrating from 1 to 4 the function negative 3 t squared plus 18t plus 15. Now I'm not doing this over dx. These variables are t's, so we're integrating over t. Remember, this dt basically counts as the width, the function counts as the height, and this integration symbol says we are adding infinitely many rectangles from 1 to 4. Where again, the parentheses is the height, the dt is the width. Well, we're just going to do our straight up calculus. Power rules. Add 1 to each exponent, divide by the same value. So that's negative 3, that stays. The t squared becomes t cubed. Since that exponent is now a 3, we divide by the same. Plus 18t, that was a t to the first, so we add 1 and we get t squared. So that's plus 18t squared, but then divide by the same value, which is 2. Plus constant terms, when you integrate, you just throw the variable in there. So 15t, because the derivative of 15t would be 15. If you don't trust me, that was originally, because there is no t, a t to the 0. Add 1 to the exponent, you get a 1, which is here. Divide by 1, and there it is. We do not need a plus c because this is an application, this is an area. We're going between 1 and 4. Now, because of that, some people like to put this in parentheses. Some people say you don't have to. I actually say you don't have to. But again, some people will put this in parentheses in case you might think, oh, we're only evaluating the 15t. That's not correct. I am handling all of the terms between 1 and 4. So we're going to plug in the upper limit, which is 4. Let me actually simplify this first. The negative 3 and the 3 cancel. The 18 and 2 make a 9. That's negative t cubed plus 9t squared plus 15t, evaluated from 1 to 4. So plug in the 4. That's negative 4 cubed plus 9 times 4 squared plus 15 times 4. Then subtract the lower limit. So minus multiple terms. Let's go ahead and get the parentheses out of the way so we don't fake missing it or actually miss it. Now we plug in the 1. So that's negative 1 cubed plus 9 times 1 plus 15 times 1. 4 cubed is 64, so that's negative 64. Now there was no parentheses, so the even or oddness of that exponent doesn't matter. That would be a negative no matter what. Plus 4 squared is 16. 16 times 9 is what? 144. Plus 15 times 4 is 60. The 1 cubed is 1, 9 times 1 is 9, 15 times 1 is 15. This went negative, positive, positive. Distributing the negative makes it go positive, negative, negative. You're distributing the negative, so all signs change. So this negative times the negative makes that a positive. 1 cubed is 1. This negative times that positive gives a negative. 9 times 1 is 9. This negative times this positive makes a negative. 15 times 1 is 15. And then we just keep doing our arithmetic. Negative 64 and 60 make a negative 4. 144 minus 4 is 140. That's 141. And then minus another 24 would be 117. That number gives us our answer. So what that says is, between 10 a.m. and 1 p.m., our technician can test 117 people. Integrating a rate gives you an actual value. How did we know this was a rate? We literally had the word rate. But if you don't have the word rate, the clue is per. When you see the word per, P-E-R, not like a kitty cat, P-E-R, not P-U-R, that tells you it's a rate. When you're given rates, you are typically going to integrate if you're asked a question about something involving that rate. So how many people, blah, 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 the rate involved people per hour. So you're integrating over time because it says people per time to get a total people. Total acclimation or accumulation of a rate is the integration of the rate over the appropriate variable. So what a lot of students will accidentally do at first is they'll just plug in the 1 and the 4 into the given function and subtract those. No, you have to integrate the rate. Now again, your calculator could have done all that for you. Because this is a nice whole number, if you actually go to second calc, option 7, and go from 1 as the lower limit to 4 the upper limit, it'll confirm that you get 117 people done basically during your peak productivity times. Now, you're definitely more productive from the next hour, but then you go back to being slower than you were starting at 10 a.m. So if you wanted to know how many people you would get done in that first hour, it would be less than the second hour. It would be less than the third hour. But then from the third hour on, your productivity starts going down. So how many people can you test in the whole day? Let's just see that. So let's do second calc. Let's go option 7. Let's see how many people we can test over this entire day, starting at hour 0, which is 9 a.m., to hour 6, which would be 3 p.m. So now it'll shade the whole thing. And we can see that we can test 198 people out of the entire day. Let me clear my screen by doing this so we can get the graph fresh. Let's see how many people we can test in the first hour. So let's integrate from 0 to 1. 0, 1. So in the first hour, we can test 23 people. How about from the first to second hour? Now this black box is still going to be there unless I go back and just type something so it starts fresh. The calculator doesn't delete the previous areas. So now we had 23 during the first hour. Let's see how many people we get done from hour 1 to 2. So during the second hour. So lower limit 1, upper limit 2. So during our second hour from 10 a.m. to 11 people, we're able to get 35. So we got 23 during the first, and then we pick up 35 in the second. Maybe this doesn't have to do with our productivity as in terms of being lazy or hungry. Maybe this is just the influx of people. Maybe it's not that many people at first, and as we get closer to noon, people on their lunch breaks, you got more traffic coming in. That's another side of the productivity there. So we got 23 from the first hour, 35 from the second hour. How about the third hour? So 23, then 35. How about from hour 2 to hour 3? 41 people. So from hour 2 to 3, we're able to knock out 41 people. Now, this graph looks symmetric based off of the halfway point of noon. It looks like the left side matches the right side. It's not symmetric to any axis. It's symmetric to this peak right here. I'm willing to bet you that if I go from the next hour, I get another 41 people. So let's go from hour 3 to 4. Look at that, 41 people. And then the next one would be, I think it was 35, and then the next one would be 23. So that's how many people we can get for each individual hour. So if you added up hours from 10 to 11, 11 to 12, and 12 to 1, which were 35, 41, and 41, you get 117. So if you add the 35 from hour at 10 a.m. to 11 a.m., 41 from 11 a.m. to 12 a.m., and then the 41 from noon to 1 p.m., you get your 117 people. Guess what? This technician could be testing for a virus going around right now. You can see curves in the media that deal with this. You see the rate of how many people per day are being tested, maybe as a moving average or maybe as an actual finite value. The finite value is kind of crappy because you tend to get a lot more testing on Monday because people aren't testing over the weekend. And that's why they say the moving average graphs are the best. So how do they find out the total number of people that have been tested? They integrate the moving average curve. That's exactly how it's done. It's calculus. And you might say, well, couldn't they just add up everybody? They could, but it's going to take a lot longer to add up all the individual tests than to just integrate over a curve. Now, do they have actual polynomial functions for those moving averages? No, they don't know the exact function that makes the shape because it's a weird, wacky, super crazy shape. So you know what they do? They go back to numerical methods. They have infinitely many of those little rectangles, and I don't mean infinitely, they have like 100,000 of those little rectangles, and they let a computer program find all those 100,000 or million areas, add them up, and then they get the total number of people infected. So this is really good stuff. And I usually don't do an infection problem for this class, but it seemed relative this semester, so I did. I usually do more economic stuff, but like I said, I really like this. I actually took an economic problem and put a, a twist on it. This used to be an economics problem. I made it an infection problem. So we only have like 5 minutes left. I don't think that's really enough time to start the next section. I think we're good at this point. So that is 5.3. Excuse me, 4.3. So we have finished 4.3. So 4.3's homework is going to be due, let's say the 7th, so that's the 14th. I'll load that assignment and give it the due date. Remember that I said the class for, so that's next Tuesday. The following class next Thursday, I will be pre-recording it. You will not see me go live that day. I'm sorry for that, but I will still make sure that you get 100% of the lecture that you were supposed to be, and we'll have it available during the live lectures period as well. In addition to having it a little before if you want to have it before. So I think that's way better than nothing, especially better than having a substitute. I was never a fan of substitutes. I like doing everything myself. You know, they say if you want a job done right, do it yourself, that kind of idea. And I'm not saying that my substitute teachers were never good. I just want to make sure that everything's done my way. So have a good day. Those of you who took the test, again, A's, B's, and C's, never going to complain for that. If you didn't take the test, if you are still going to continue to stay in this course, please make sure you do test 3 in the final because you don't want to have a bunch of zeros. If you have any questions, email me. Besides that, we'll see you on Thursday. Take care, everyone.